Assalamualaikum warahmatullahi wabarakatuh and good afternoon everyone. Okay, um, how many students do I have in this group? Wait. Alright, so before we start, do you have anything to say in regards to your, let me try and see what they are, the group members. So for the group members, every one of you have a group already, yes? For this one? Is it, am I lagging, class? Because somehow my internet is kind of slow right now. Okay. Right, so I think it's just maybe perhaps Google is a little bit slow. Okay, so I should have at least 36 in my class since I have 6 group. At most 36 because I have 6 group. Okay, um, all right, never mind. So, I guess for group 3, there shouldn't be any problem with the how do you call that, the groupings, okay, for the group project as well as the lab viva. Okay, oh yeah, so let me start recording. I don't know whether I mean this is necessary, but why not? Okay. All right. Okay. So today we're going to be looking at tutorial 5. So as usual, we are going to be doing this on our Google Docs. Okay. As we have seen in our lecture on Tuesday, okay, whereby we have looked into a divide and conquer algorithms, okay, whereby as if you remember, when we talk about the divide and conquer approach, all the algorithm will have the 3 distinct stages. Do you still remember what are the stages, class? For the divide and conquer? Still remember? We have the, what are the 3 stages for divide and conquer approach?
Divide, conquer, combine.
Divide, conquer, and combine. Okay. So, so those are the 3 distinct stages if, like, let's say you want to apply the divide and conquer approach for solving your problem. Okay, so I think for question 1, since we from your feedback, you have done merge sort and quick sort before in your data structure class, right? So I'm not so too worried, but let's go through this question. Uh, um, I mean, it's not too I guess it's not going to be too critical. Maybe some of you might not be able to do this. But yeah, can I have the answer for question number 1? So like, let's say we have the array 85, 34, 63, 45, 17, 81, 96, and 50. And we are supposed to, we are going to do merge sort and quick sort on this input. Okay, so can I have someone to share the answer for this one? So do you remember what are the three steps for the merge sort? What happened in the dividing of the merge sort? What happened in the conquering stage of the sorry, conquering stage of the merge sort as well as the combining stage? Somebody is actually doing this real time. No, Ma, you just do it. If you can do it right now, yeah. And put yes, yes, somebody cheering for you. So one of your friend is actually doing this real time. It would be nice if you know, like whoever that is doing it right now to actually explain it, what you are doing. Switch on your mic and just like explain it. Okay. We also have another answer down there, but it's quite nice to see the process here. And then what happened? After that, what happened? Okay, you compare between those two elements, and then you get 2485. And then you compare 63 with 45. So we got 45 and 63, and then you compare 17 with 31, we get 17 and 31. Compare 96 with 50, you got 50 and 96. And then after that, we compare. Let me be the voiceover for this. And then we compare between the 24, 85, 45, 63. We compare 24, 45, we get 24. And then we compare 85, 45, we get 45. We compare 45 and 63, we get we get 45. We compare 85 with 63, we got 63 and 85. 17 and 50, 17. 31 and 50, 31. 50 and 96, 50 and 96. And then the last would be comparing between these two sub-array, which is 24, 17, we got 17. 24, 31, we get 24. 45, 31, we got 31. 45, 50, we got 31. 60, sorry, 45, 50, we got 45. 63, 50, we got 50. 63, 96, we got 63. 85, 96, we got 85. And finally, we got 60, 96. Okay, so that is how you do the merge sort. So basically, in the merge sort, the dividing stage is very trivial. Meaning, in a sense, if like let's say you have your input element, all you have to do is just keep breaking the array into two sub-array, okay, until you get this individual element, and then after that you combine it back. Okay, that is when you will do the sorting. Okay, where will you will do the comparison between the two sub-element and then combine it back a into one array. Okay, so this is another example so that it is a little bit clearer. Okay, whereby you have this arrow, so you can see how it is actually breaking up and is being combined back. Okay, so normally if you are implementing this, it doesn't occur like stage by stage. You're probably going to see that you are going to go to the right side, and then you will break it on this side, and then you combine it back, and so on and so forth. So it's just that during the implementation, you're probably going to see that one side of the how do you call that, one side of the sorting is going to happen first before it goes to the other side. Okay, so it's just that when we explain the concept of merge sort, like we keep breaking it down like one by one. All right, but that is for you to have a look at the real implementation of the merge sort. Right. uh okay, quick sort. Yes. So quick sort, we have three stages as well: the divide, conquer, and then combine. For merge sort, the dividing is trivial. Okay, and then you do your and then after that, after you dividing, and then you recursively break the array into two subarrays, and then the combining part is where you will do the comparison and merge it back, right? So for quick sort, the dividing is the one that will play a major role in the sorting algorithm, okay, whereby we will do the partition. All right. And the combining stage is where it will be trivial. All right. So can we try and see some answer from you for quick sort? Anybody? Class? I'm waiting. Or do we have someone to actually do it real time again? Come, let's go. Yeah, why not? Like you can always do it real time. Okay, who wants to who can give me one answer? Class? I'm okay. Yeah. Mm, okay. Both is the pivot. Okay. So this is a different way of doing the quick sort. Okay. So because when the one that we learn in class is a little bit simpler, because we just like take the last element in our array, and then we make it as the x value, which is the pivot value. And then after that, we have the ing moving together, meaning moving in the same direction. All we have to do is just compare the x and the j, and then we move the ing, the pointer. But you will see for this one, it is a little bit different. Okay, the way that this algorithm does, because I think you will see that the way that it compares is not with the last one, but it is with the one before, and then it will like start moving towards each other. Yellow is comparing. How come you have the same answer like the previous class? Can you give me the video that maybe you can share the link to the video that you learn this algorithm? Maybe you can continue first this one, and then your friend can see what am I actually talking about. Yeah. It is actually still comparing with the x actually, which is 45. It's just that the I and j is moving towards each other. Class? Sorry. What happened to the real time? Okay, he or she is giving you the link to the YouTube video. So you will see that how the comparing is a little bit different. It's not so much of difference. It's just that your pointer is moving towards each other rather than moving to the moving in the same direction, because I believe that you are still comparing between 45. I'm not sure whether you're comparing the pivot with 85 or you're comparing the pivot with 96. So it depends on the algorithm that they're using for this one. Do you have any question? Or you're not sure what am I referring to? So 85 is bigger than 31. Why are you comparing with 85? Okay, oh, you're switching as like that. Will it work? In that case, never mind, continue. Just continue, and then we will see. Let me try. Because right now it's very difficult to see what is he's doing, is because we don't know what is the pseudocode look like. So I'm trying to guess. So right now he is he or she is, I don't know whether you're a he or a she. So please forgive me if you're what okay, so you're comparing 85 with 31. Okay. Okay. And then you swap, since 85 and 31, 85 is bigger than 31. And then you compare 24 with 85. It is smaller, then nothing happened. The next one, you compare with what? And then you compare, which one with what? 24, 63 with 85. Okay. The way you compare is a little bit questionable. Because I can see that why suddenly you are comparing 50 with 85, because your pivot is 45. Your pivot value is 45, but then you're comparing it with 85, 50. Okay, and then continue, just continue. Let me try and how do you call that? See the link. Or does it actually do? Anybody else got the answer for this one? Maybe you want to share? Oh, this lady. Okay, from HackerRank. Quick sort pivot. Okay. So right, left. Okay. All right. Okay. So quick sort. What is the coding? Quick sort array. Okay. I want to see what is the partition. Okay. All right. While left is lesser than right, left plus plus, Swap array left, right. Okay. Okay. No, it is actually uh they are not comparing 85 with 31. If you look into the coding, from the link that you give, okay, for those of you who wants to see it, if you look at the how do you call that, at the uh 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 code here, when they do the partition, while left is less than right, it is actually comparing between array left and the pivot. That's why I said there must be something wrong, because you're comparing it with 85 and 31. You're not doing anything with 45. So you're still comparing it, you're supposed to compare it with 45. Do you get what I mean? Because else you're not going to be able to partition it properly. Let me screenshot my screen so that I can paste it and tell you what I mean by that. So this is from, wait 1 second, I don't think so it's this one. Let's see if I can make this bigger a little bit and I can get the whole screen. No, I think that would be the only thing that would be the biggest. Okay, so let's see if I can screenshot this and put it here. Can I? Or do I still need to uh oh no, this is the link. 1 second. Um let's see if I can insert um the stop. Yeah. Do you see this one? So from the coding here, okay, from the link, you see this one is actually comparing between array left, the one that is coming from the left, it is comparing with the pivot, and then the pointer will be moving. So that's why just now the right pointer is yeah, the right pointer is 50. You can actually change 45 to the end. But then just now, because you are comparing it with just now you're comparing it with why did you can I see the one that you put just now? Why did you delete it? Uh, that's why don't delete. So you see, the reason why I said it's wrong is because of this thing. 85 is not with 31. You're supposed to compare it 45. The pivot. Ah, okay. So come, who wants to do this real time since you have the coding here already? So the only difference here is that the pointer left and right. What we did in our class, we have uh we have I and J moving in the same direction. But in this case, it has left and right that is moving toward each other. But then the comparison is the one with the left and the pivot. It is still the same. It's just that the pointer is moving towards each other and the one in our class is moving in the same direction. So left pointer 85, right pointer is 50. No, right pointer is 96 now. Right pointer is at 96. I mean in for the second line. So once you swap left pointer, right pointer, after you swap 85 is more than 45, stop the left pointer. Yeah, you don't do anything. Unless it is less. Mm. There are so many while. So you have two while loop. That's why the one that I give inside the class is much more easy because it's the step by step. Because this one you have two while running at the same time. So while array left, while, yeah. So you need to check both. While left is less than equals to right, left is 85. You saw 81, 85. Just one time. Exam. Okay. So this one is the one that we do inside the class, right? The one that you post here, right? Okay, so I don't really understand what do you mean by the right pointer is at 50 because you already choose your pivot is 45. I will get back to you later. Okay, so in line one, this one, right? You're seeing the line one, right? So you already see that the pivot is the bold one, meaning it is 45, right? And then in the second line, you swap 45 with 50. So now the pivot is here. Your pivot value. So where is so you see this one? The pivot is actually here, 45. Okay. And then your left is here at 85. And then your right is here at 96. So looking at the question, this one, let me move this up, um, up here so that I can easily explain. Okay, so now, so we need to see the while array left. So 85 is less than pivot, right? You move the left. So now you are going to compare 24. So now the next will be comparing 24, and then array right is more than pivot. Right minus minus. So the next one will not be comparing 85. So where should I? Uh, so so now the next step is comparing 24 with 31. And now you do the same again. You see whether 24 is bigger than 45. No. So sorry, while array left is less than pivot. So while array left is less than pivot, but then it's not, so it's supposed to be 85. Still 85, sorry. So it still be 85. And now so 85 while array left is okay, so 85 and 31. So now 85 with 45, it's still bigger, so stay. 31 and 45 is how do you actually do that? While left is less than pivot, left plus plus, left plus plus, right minus minus. So then if left is less than right, swap. Oh, okay. So there's an if here. I saw this one. Okay, so then 85, so left is less than right. Swap, swap left, right, left plus plus, right minus minus. Okay, I see. So this algorithm, there's a swap there. So when it goes to check 85, 95, so uh I totally understand now. So 85, okay. So I need to understand. Left is smaller than the pivot, which is not. So it's not moving. Right is bigger than the pivot. Yes. So yes, so now 31 and 85. And then you compare if left is smaller than right, swap. But then this one, it is not, right? The second line. Please go through this line algorithm with me, right? Am I doing this right? So since this one is not, left is not smaller than right, and then nothing happened. So left is not smaller than right. Swap. If left is smaller equals to right, but then it is not. Why do you swap? Array right is big. Oh, okay. So this one. Okay. So it is actually this one. Array right is bigger than pivot because it's bigger than 45. So if left is smaller than right, and then you swap. So now 96 is going. Why are you swapping? Left is smaller than right. Swap array. Left, right. Now I'm confused. Can someone like for this one, can you like switch on your mic and try to run this? So left, right. I think I'm missing something here. What is the swap function here? Mm, I'm trying to see the swap. So what is the swap? With array left, right. Uh, array left, array right pivot. Left, right. Pivot, okay. Don't do this. Why is it connected to somewhere else? Give me the whole answer for this one. Is this the whole answer? We haven't finished doing the partition. So now what happened? Where's the 45? The last line? Where's the answer just now? The other one? Where's the other answer? The quick sort answer? Don't delete your answer, please. There's nothing wrong with that answer just now. This one is the one that we have in class. So it's very easy because our I and J is like moving. So it's not too complex. You know, you only compare one. And if that thing happens, you know, like it's just a 3-step. But this one is also very simple. It's just that I need to understand how the pointer is moving. But now it's like saying the right pointer is 50. I'm trying to understand your friend's answer. That's why I said, whoever that is doing this answer, can you please switch on the mic and explain a little bit, maybe? No, he's gone. Or she's gone. Klaus, are you still there? Yeah.
Yes, still here. I think they must be gone, probably.
He or she must have got scared. No,
Yeah.
I mean, the algorithm is this. The concept is the same. It's just that because I did notice that that for this algorithm, there's this if statement. Okay, so if there's this statement, and then there must be something to do with the swapping. So we have 85. So he swapped 81 with 85. And then 24 with 85, but then 24, okay, so this one left is smaller than right, so you don't, which one is left, which one is right? If left is less than equals to right, then swap array left, right, so left plus plus, but this one we are not swapping, or did I miss anything? So or is it left pointer? So is it that I understand this wrong? And then you move left, right, right has to be moving. Yeah. And then you compare, this one is smaller, and then you swap. So basically this one have to swap, right? Whoever that is doing this, can we continue? Can we continue? Right pointer is at 50. 50 is bigger than 45. Move the right forward pointer to 96. Then 96 bigger than 45. Move the pointer to 31. Swap 85 and 31. Do you see the reason why I don't use this algorithm, rather I use the one in the lecture? Okay, can we continue? I'm waiting. I think you were following the one from the video properly. It's just that I think I missed out something here. So I'm not so sure if it is the same question or not, because I'm not looking at the whole video. I'm just screenshot like uh uh through the thing. Can we finish this quickly? It's already half an hour. We are still in question 1. You're not gonna finish it. Now you're confused. Okay, never mind. Maybe the class you can actually go and look at the video. I will look at the video as well, and perhaps during the class I would or maybe I will like address this during the lecture. The previous class is also using this algorithm. It's just that I did not see the video, and I don't have this code, so that's why I'm not as confused. So I will get back to you in regards to this one. So maybe if you can finish this one until the last until the end, it would be nice. Okay, so that I can see. So maybe we look at this answer. Okay, this is like what we have in our class, the algorithm, I believe, because the pivot is the last element in the array. So what you do is that you compare the element with the pivot, and then if let's say it is smaller, you move the j, and so on and so forth. So the four steps that I show inside the class. So I think this one is like the one that I have. But then why your 24 is being swapped? This is another algorithm. So 85, 40. Okay, yeah. So 24. Uh, so you swap 24. Okay. All right. So this is the answer according to the algorithm that we use in class. Okay. It's just this one. I probably need to go and look at the video and try and understand how the things work, because I think I got confused a little bit in terms of how they swap the element inside the array. Okay. All right. So let's go to question number 2. The set 145. So far, are you okay with the quick sort class? How many of you here? Because this class is always very quiet. Class, are you okay with the quick sort?
I think we'll have to read more.
Right. We have to do it now. Have you tried this? Have you tried this? Class, you need to try this before we go into the tutorial. Then we can understand, or we know what to discuss. Okay, like this one, right? So we have this, and then suddenly, like you have a different answer, and then we can always discuss this. Okay, and for algorithm, you will find a variety of algorithm, like for example the quick sort. You will see that there is a different implementation. I believe this one is the original Hoare algorithm, whereby it allows duplication in the array. Okay, because of the way it is being compared. Okay, rather than the one that we see in class, but it's a little bit more easier to do the one that we have in our lecture. Okay, so I believe this one is actually the original, not the original, but the one that Horst proposed. Okay, and I believe this one allows duplication in the array. Okay, but I need to check if this is actually the real one. I know that the original one, the way they compare is a little bit complex, because they want to allow the duplication. I'll try and check whether this is actually the original one. I had a feeling this is actually the original one, but I'm going. I will verify this again with you, inshallah, during the lecture next week. Okay. All right. So for question number 2, so we are supposed to draw this binary search tree of height 2, 3, 4, 5, and 6. Okay. So one of your friend already give the answer. So who does not know how to do this? I know you can get the answer from this one. than 4. Me. Okay. All right. So, okay. All right. So, let me share my um iPad. Not this one. Mm, okay. Um. Okay. Let me show one very quickly. I need a quick look. All right. All right. So let me stop sharing this one first, and let me share my screen over here. Okay. All right. So if you know, okay. So all right. So for this one, right? Uh, as you know, as I mentioned, I believe I mentioned this in class. In order for you to know what is the height of a tree, is that if like, let's say you have this tree, the height of this tree is, this would be level 0, this would be level 1, and this will be level 2, and therefore the height of this tree is equals to 2. Okay, so in this question, it says that if like, let's say you have a set of elements, we have 1, 4, 5, 10, 16, 17, and 21. Okay, so this is a set. Remember, it's not an array. If you, let's say if you have this set of element and we want to draw a binary search tree of height 2, 3, 4, 5, and 6. Okay, so before we do this, you have to know the binary search tree. The property of a binary search tree is that if like, let's say you have a parent and the left child and the right child, okay, this is your P, this is your left, this is your right. So if like, so you have to make sure that if like, let's say you have X in your parent, the left child will be smaller than the X, the right child will be bigger than the parent. Okay, so this is the property of a binary search tree. Okay, so in this case, how are we going to put in this element so that we're going to have a binary search tree of height 2, 3, 4, 5, and 6. Okay, so let's try and do the first one. So let's say we want to do a binary search tree of height 2. Okay, so maybe we can start with, so in this sense, perhaps we can do 10. And then maybe yeah, we'll just follow this one, so we can put uh 4 here. This would be 1, this would be 5, this one we can have 17, we can have this one 16, and we can have this one 21. So if you look at this tree, is this tree following this property, class? This is the parent, the left side is smaller, the right side is bigger. This is the parent, the left side is smaller, the right side is bigger. This is the parent, the left side is smaller, the right side is bigger. Okay, and the height of this tree is 0, 1, 2. Okay, so what if we want to draw a tree of height 3, let's say for example. Okay, so from the same set, we can actually build this tree into, maybe we can start with, I don't know, maybe we can start with 4, and then we can have 5 here. Maybe we can put 1 over here, and we can go, I don't know, maybe we can go 10 over here, and then maybe we can go uh, maybe we can go 17, and then 16. Oh, sorry. Yeah, yeah. Yes, 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 yes. Thank you for reminding me that. Thank you, thank you. So maybe we can start. Oh, I think I should start with 17 then. So 17. Mm, uh, how do we extend it? Maybe we can start with 10. 10, and then we can put 5 over here, and then we go to the left with 4, and then we go to the left with 1. So we have height 1, 2, 3, 0, 1, 2, 3. Okay, so we can do the same thing on this side as well. So we can do of 17, we can do 16, we can do 21. Okay, so this is of height 3. So because this one is level 0, this is level 1, this is level 2, and this is level 3. You're probably going to get a different 3. So yeah, so if you look at the answer in the drive, so one of your friend, how they got the 3 is they got a different 3. Okay, and then try to do the same thing for height 4, 5, and 6. Can you try? The reason, okay, maybe I should explain to you the reason why you can have this kind of thing. Okay, so for binary search tree, okay, so as the uh the look of the tree that you're gonna get, okay, with a binary search tree, it depends on the sequence, okay, on the sequence of element that would be inserted into the binary search tree. Okay, so in this case, it is showing that even though you have the same set, the same element inside the tree, but due to the sequence, okay, the sequence of the element, you will get a different kind of tree. Okay, so in this case, like let's say for example, let's say for example, we randomly start, we say we have 4 coming in first. So the 4 would be the root, and then let's say 10 comes in. So the 10 would be on the left side. Let's say 1 comes in, you're going to go to the left side. So this one would be 1. And then the next one would be 17, let's say for example. So 4, sorry. Yeah, so 4, yeah, yes. Why are you saying, yeah, I just realized, I think I mixed up just now. I think one of your friend said that the basic rule. Just now, Gori, I saw your text. Why you say it's not following the basic rule? Okay, so now 4 is uh 10 is bigger than 4. So it's, I'm not breaking any rule. Okay, so like let's say the next one 17's come in. 17 comes in. So 17 will go this way. Let's say the next one 16 come in. 16 is 16. So it can go 16 here. It was before. I don't remember what is the before one. Okay. So so in a sense, you see the tree will look different. It depends on the array that you get. So this one just now, what is the array looks like? So for, let's say 10, and then we have 1, and then we have 17, and we have 16. Let's say we change it a little bit. Let's say we have 17, 10, 1, 4, 16. Let's say, for example, and let's see what kind of 3 do we get. So we're going to get 17. We're going to get 10. We're going to get 1. And then we're going to get 4. And then we're going to get 10. We're going to get 16. Do you see what I'm trying to say here, class? Is it okay? So for binary search tree, it's just saying that for the same set, you can actually get a different looking tree just by this just by, you know, if you have a different sequence, you probably going to get a different looking tree. Okay, so as you can see here, for this one and this one, it has the same set, but because of the sequence is different, this one you're going to get this tree, but this one you're going to get this tree. Okay, so did I check? So this one is small, this one smaller, this one smaller, this one is bigger, this one is bigger than this. Yeah. Okay, so this is a binary search tree. Are you okay so far for this question? For this one? I saw a very quick me just. Is that me okay? Or are you still do you still need to for me to explain this one further? Is that alright? Class?
All good for me.
Okay. All right. So that is for question number 2. Okay. So you again, as I mentioned, you're probably going to get a different answer, but as long as you keep the property of a binary search tree whereby the left is smaller than the parent and the right is bigger than the parent, then you should be good. Okay. All right, so these are some of the example answer that you can get for binary search tree of height 2, 5, 2, 3, 4, 5, and 6. Okay, this is the 6th one. Okay, so that is for that question. Yeah, so one of your friend have this. So 1, 1, 2, 0, 1, 2, 3, 4, 5, 6. Okay, so here we have 2 variation already. Okay, of height 5, height 6. All right. Is this correct? So 10, 4, 17, 4, 1, 5, 17, 16, 21, 10, 5, 10, 17, 5, 4, 1, 17, 16, 21. Yep. 5, 4, 21, 4, 1, 21, 17, 16, 10. Yep. 4, 1, 4, 21, 17, 16, 10, 5. Yes. 1, 21, 17, 16, 10, 5, 4. Okay. All right. This is good. Yes, this is correct. Okay. So this is another answer for the binary search tree. Okay. So question number 3. Is the array with values 23, 17, 14, 6, 13, 10, 1, 5, 7, 12 is a max heap? What is a dot length and a dot heap size for this array? Okay, so one of you have already provided me with an answer whereby a is not a max heap, length is 10, the a heap size is 8. Okay, so anybody got a different answer? Anybody do not know how to get this answer? What is a dot length? A dot length is the size of the array. So in this case, the size of the array is 10. But a dot heap size is 8. Do you know how do you get the 8? I get the 8, class? Um, Anybody don't know how to get the 8? Don't know. Yes. Like if you don't know, you please answer me quickly. Then we are not going to waste any time. How to get hip size? Okay. All right. So again, let me change back to my iPad. Okay. All right. So okay. So we have 23, 17, 14, 6, 13, 10, 1, 5, 7, 12. Okay. So if we put it inside a heap, so we're gonna get 23. We're gonna get 17, 14, 6, 13, 10, 1, 5, 7, 12, right? So basically this is what we're gonna get. So we're gonna get this 3. What is the property of a max heap? Do you remember what is the rule for having a max heap? What is the rule for having a max heap? The
The parent
parent,
node will be greater than the child node.
the child node, right? Okay, so let's check. For this one, is it okay? It's okay, right? It's bigger than the child node. Okay. This one, it is also bigger than the child node. So this one is okay. This one, is it bigger than the child node? Yes. This one, is it bigger than the child node? It's not, right? Because this one is bigger than the parent, right? So if we look inside the array, so we continue and we look here. This one, uh, yeah, it is still okay. But then after this, since this one already violate the max heap, so we can say that this one is already like out of the heap, okay? And therefore, we can count how many element inside this heap, which is 1, 2, 3, 4, 5, 6, 7, 8. And that is how you get the heap size. So basically inside your array here, the a dot length is equals to 10, but the a dot uh, heap size is only 8, because only the 8 element is following the max heap property. Is that okay? Is that right? Are you good? Yeah. So that is for question number 3. How to get the heap size. Does that answer your question? Yes or no?
Yes, yes, doctor.
Okay. All right. So for question number 4, illustrate the operation of maxipify on array A. Anybody can share the answer on this one? Anybody wants to share the answer with for this one? Class, come. Nobody does the tutorial, is it? Try to do the tutorial before you come to the tutorial session. Else, it's just like the lecture. You are not going to get, like make the head of the or the tail in the discussion. Class, question 4. Maxipify on array A. Quickly, if you're doing it on paper, snap and post. That sounds like some kind of TikTok dance that we can do. Snap and post. I don't do TikTok though, but come. Nobody? Class, let's go. Question number 4. I have how many students right now? I have how many? I have 28. I'm sure one of you have the answer. Don't tell me all 28 of you is not haven't done the tutorial. Come, nobody is going to know. It's another TikTok. Yeah. Oh my god. Okay. All right. Okay. So thank you. All right. So in this case, do you still remember what this Max CP5 is used for, class? Max CP5 used for what?
To sort the value in ascending order, I guess.
Max CP5? I don't think Max CP5 is used to do the sorting. Heap sort is the one that we do to.
Oh yeah, but if after we do the max CP5 and then we do sorting, then we will get the ascending order. So max CP5 is like to move, to make all the parent node become greater than the child node. Yeah.
Okay, so then what about build max heap? What is the difference between max CP5 and build max heap?
Is max CP5 for turning an array into a heap?
Not really. No. So the difference between max CP5 and build max heap is that max CP5, the purpose of that function is just to maintain the property. They don't build anything. They just like go through the element and check whether the property holds. But for the build max heap, you are actually building the max heap using the max CP5. I hope that does not confuse you. So that is the difference between max CP5 and build max heap. Max CP5 is to maintain the property of max heap. Okay, so in this case, so like let's say we have this array, okay, and then we put it inside the tree. So 27, 17, 3, 16, 13, 10, 1. Okay, so 1, 5, 7, 2, 4, 8, 0. Okay. So max CP5, you check it from the top. Normally we check it from the top, okay, to see whether the property holds. Okay. So in this case, 27, 17, 3 is okay. 17, 16, 13 is okay. 3, 10, and 1 is not okay, right? Because you have 10 that is bigger than 3. So you have to sort this one up. So the next one, the 3 should become 10. And then 3 is down here. And then you're going to do the max CP5 again to check whether the 3 here is max heap. Okay, I think I better, or anybody got another answer? Okay. This one you're checking. I don't understand what do you mean by the check marks, but here I see that so 37, 3. So there's something wrong here, and then you swap, and then once you swap, you check with so in a sense you swap it with the biggest children up. So 10 is the biggest children. Now 3 is down. So again, you check with the child, and then you see that it is smaller than the children, and you choose the biggest children, either left or right. So now the right one is bigger, so you swap it with 9. So this one is okay already, and then you go to the next one, 16. The property is okay, it still checks. 13, it's still okay. This one we check already, and this one is fine. Okay, so I'm not so sure what are you doing for this one. Uh,
Excuse me, doctor.
yes.
Uh, I thought that Maxify check from the half of the middle of the array. So that's why I check it from 1, 10, 13, 16.
I see. Let me try to check back. Max CP5, I thought you have to start from the top. So Max CP5, because build Max Heap, yes, you try to find the question asks Operation Max CP5 on array A. So normally we check from the top. So normally for Max CP5 is we check from the top. For build Max Heap, yes. Build Max Heap, you need to find it from the middle of the how do you call that? The middle of the heap. Okay. And AI, A left, right, if L is smaller than largest, L largest, yeah. So basically you will start with the first, you will start with the parent, okay? Because you're going to check the left and right. I think for the Max CP5, for this question, it doesn't matter if you check it from, if you're doing it like a build max heap. But normally you will check it from the root. And then you once you check from the root, and then you will traverse down. Because Max CP5 is, you have to traverse down, okay? Alright. Oh, write a pseudocode for min hippify. Did I skip this question in the previous class? I don't remember doing this question in the previous class. Okay, so any question in regards to the Max CP5 class? It's okay, right? So basically the step for Max CP5 is that you look at the parent node, you look at the left, you look at the right. If it is, if you have any left or right children that is bigger than the parent, you need to find what is the largest, which one is the largest child, and you have to swap it with the parent. Okay, so that is the step for Max CP5. All right. So the pseudocode for min hippify, so it's just that you flip the property around. Okay, so basically you check that the child has to be bigger than the parent. Okay. So this is the, I can give you the answer because I think this one is quite simple. Okay. So yeah, somebody already gave me the answer. Yeah. So basically you check if hip size L is smallest, yes. You find what is the smallest, okay? And then the smallest would be the how do you call that? The parent, okay? All right. So if you notice, even in the algorithm as well, it is actually going down. Okay, you call the minipify to the one that just now the maxipify, we change with the, what is the word for the this one, maxipify A largest, exchange AI with largest AI. If L, A heap size and A left is bigger than AI, largest is L. L's largest is I. If exchange A with largest, max CP5. Yeah. So you're actually going down. You're going to at the moment the largest is actually one of the child. So you actually max CP5 going down. Okay, same goes for this one. The smallest is actually one of the children. So you're going to mean HPFI going down. Okay. So that is this is actually the algorithm for mean HPFI. Okay. So the difference is that you're going to check whether the left child is smaller than the parent. Okay, the AI. So then we keep track of which one is the smallest, and we're gonna swap up the smallest between the two children, okay, as the parent. Okay, so how about the question number 6? I think this one is pretty straightforward. Question number 6, write an efficient maxipify that uses iterative control loop instead of a recursion. Do you have the answer? Or do you want my answer? Because I think this is just a practice for you to change from recursive function to iterative function. I think we've done this before quite a few times, so I'm not gonna like spend too much time on this one. So I can give you the answer for this one. Why is my cursor is not working? Okay, so that is the iterative maxipify. Okay, and if you have any other answer, you can post it as well. Okay, so that is for question number 6. All right. So question number 7, now we need to illustrate the operation of build max heap on the array A. Okay, so just now as I mentioned, for the max CP5, normally you look at the parent and your max CP5 is going down. So now for the build max heap is the one that you will have to find what is the what is the last, which node is the last parent in the tree. Okay, so that's why we have to do the AND over 2 operation. So can someone share me the answer for build max heap? Class? Quickly, we have 3 more questions. I think we can finish this one early. Question 7. Quick, 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 quick. Everybody should get ready with the answer. Build max heap. I'm waiting. Nobody? Come, I have almost 30 student, 30 people inside here. So I'm sure one of you have the answer. Whether it's nice or not, it doesn't matter because as I mentioned, nobody's gonna know. Okay. All right. So for IA length divided by 2 to
Doctor, you are muted.
why am I muted? Okay. There's 9 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. The question, you're missing 9, but it's okay. But yeah, you're missing the element 9. But I think it will be alright. Okay. So basically you need to max CP5 from so since this one is 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 2, which is 4. So we're going to do max CP5 from node number 4, okay, up until node number 1. Okay, so let's look at this one at node number 4. Max heap is not it's not max heap, so we're gonna run max CP5 on this node. So we're gonna find, supposedly there's a 9 here. Okay, so basically we're gonna swap 22 up and 10 is gonna be down. Okay, and then we are done. And then we're gonna go to node number 3. So node number 3, we check that the max we need to run max CP5 as well, because 19 is bigger than 17. So max CP5, we look at the two children, the biggest one will be swap up. So we're gonna swap 19 with 17. Okay, and then after that 17, since they don't have any more children, so it stops here. And then we go to node number 2. Okay, so node number 2 again, the max heap, it is not max heap, so we're going to run max CP5 on node number 2. So we're going to see the children, and the largest one is going to be swap up. So therefore 84 is going to be swapped with 3. Okay, so now this is going to be 84. This one is going to be 3. Now we're going to go into node the last node, the last node, and we can see obviously that the max, it is not a max heap. So we're going to run max CP5 on node 1. We're going to look at the two children, which one is the largest. So this largest is going to be swapped with 5. So 5 is going to come down here. And we're going to check again. So now since this one is being swapped, we're going to run max CP5 on this node as well. Okay, so 5, we can see that the max heap is being violated here as well. So we're going to take whichever that is the largest, we're going to swap up. So 22 is going to be swapped up, and now we're going to get this. And then we're going to check whether the property hold. And since we found out that the children is one of the children is bigger, we're still going to do max CP5 on node number 4. And finally, we and then we swap 10 up into with 5. And yeah, and finally we're going to get our max heap. Okay, so that is how you build your max heap from an array. Okay. All right, so forgot about 9. It's fine. I mean, like at least we whatever that is being done is already being done properly. Okay, so that is how you do the max heap, build max heap. Okay. All right. Any question about this one? Nobody. Is everybody okay with this? Any question about this one? I saw there's some chat. Let me open the chat. I don't know why my PC is a bit slow. Oh, okay. I hope I'm not muted for too long last time. Okay. All right. So that is for the build max heap. Okay. You alright with this? Yeah. Class, are you okay? All right. So for question number 8, now we're going to do the heap sort. Just now, one of your friends talked about max CP5 is to do sorting. Partly, yeah, the max CP5 will be used when you do the heap sort, because you once you extract the first element, which is, because whenever you have a max heap, definitely the root would be the largest number, right? So whenever we change it with the last element, definitely we need to check back whether the max heap property still hold. Okay, so that's why the MaxCP5 is still going to be used by the heap sort. It's just that there's an additional step whereby you swap and then you reduce the size of the array, the heap size. Okay, that is why if you remember just now when we do question, I think question number which question just now that asked about the heap size and the heap um this question just now, question number 3, right? Uh, so it is quite obvious that it is being used here in the heap sort because the element size, the A dot size is still the same, but because we swap it with the last element, we need to reduce the heap size. So that the only thing that the only element that we are going to be max CP5 is just those that is within the heap size. Okay. So can I have someone share me the answer for the heap sort? Oh my god. We have seriously, come. We have 3 more questions and I think we can finish this in another 10 more minutes. I have 27, 28 in my class. I'm sure one of you have the answer. Come. I'm being very very positive. Out of the 28, I'm really hoping one of you like really do, like attempt the tutorial question. Come? Nobody? Or is the this last minute person is doing the answer right now? Come? Nobody is going to do this? All right. Thank you. Okay. So, okay. So A dot lag is 4, 5, 20, 25, 17. This is quite long. I don't think this is 2, 4, 5, 7, 13. Okay. I'm trying to okay. So where did you build your max heap? I think the last one would be here, right? So basically up until here, you have your max heap already, right? Correct me if I'm wrong. Okay, because if you notice our array, the one that is given in the question, it is not a max heap. So you have to build your max heap first. Okay, so you build your max heap, same like the operation like we have in the previous question. So this one should be with max heap. So 25, 13, 20, 13, 8, 7, 8, 5, 4, 20, 17, 2. Okay, so we already have max heap over here. So what we're going to do is that we're going to swap 25 with 25, and then we are going to reduce the heap size, and then we're going to run the max CP5 again, okay, on the first node. And when we run the max CP5, this would be the resulting tree. This one, since this one is not considered a heap anymore, it will stay as it is. And then the last element in the heap would be 5. So we're going to exchange 20 with 5. Okay, so now 20 is down here. And then we're going to reduce again the heap size. And now this is the only element in our heap. And we're going to do the max CP5 again. Okay, so once we do the max CP5 again, we're going to get this result. This one is not in the heap anymore, so it will stay as it is. And we're going to continue again swapping the first element with the last element in the heap. Okay, not in the array, in the heap. All right. So we're going to exchange 17 with 2, we're going to reduce the hip size, and we're going to do this all over and over again until we get to the first note. Okay, and once we have done until the last note, we can see that we have an increasing order: 2, 4, 5, 7, 8, 13, 17, 20, and 25. So do you have any question in terms of the hip sort, class? Class? Hip sort? What is the running time complexity for hip sort? I always forgot to ask the running time complexity. Class? Hip sort? Running time complexity for hip sort. Everybody is opening the lecture notes. And log n. All right. So if I'm in the lecture hall, I'll probably see everybody was like opening, flipping their books and trying to find what is the answer from the lecture. Okay. All right. So n log n. Okay. All right. So question number 9. So I guess this is okay since there's no question. So question number 9, we need to illustrate the operation of maxip insert into the array A. So we want to insert 10 into the array A on heap A 15, 13, 9, 5, 12, 8, 7, 4, 0, 6, 2, 1. Okay, so we're going to insert a new element inside the heap. Anybody got the answer? So is this a max heap 15, 9, 3, 3, 5, 12? I think this is already a max heap. Is it? Is this already a max heap? 15, 13, 9, 5, 12, 8, 7, 4, 0. Yep, it's already a max heap. 6, 2, 1. Yeah. So this array is already a max heap. So now we are going to add another element, which is 10, into the heap. So how are we going to do this? So I saw the wolf is trying to give the answer again. Yes? I'm waiting for the answer. Last one. So you remember the step when we want to do the insert into the heap? We create one element, okay, at the end. So in this case, what we do is that before we actually have this 10 here, we initialize it as negative infinity. Okay, so and then after that we increase the element into 10, the value into 10 over here, and then after that, once we have insert the element here, we are just going to look at the parent. Okay, so you're going to look at the parent. If the parent is smaller than the child, we are going to swap. Okay, same goes here. We just look at the parent. If the parent is smaller, then we're just going to swap. Okay, and here, look at the parent, and the parent is bigger, then we can just leave it. Okay, and then it's fine. And then we are done. That is how we insert a key into a heap. The reason why we can do this is because the heap property, we already have the max heap property. So that's all we have to do is just compare the parent. If the parent is smaller, we're just going to swap it up. Okay, so that is how you do the max heap insert. Are you all okay about this one? So the insert is not we are not going to do we don't have to do any maxipify checking for the property. We just compare it with the parents, and if the parent is smaller, swap it out. Okay? All good for this one? Yeah?
Yes,
Alright.
Doctor.
Okay, good. All right. So last question. So this one is something like you need to think of a way of how we can solve this problem. So this problem is that Mr. Tommy is keying in some student metric number into the system, and then we know that the metric number are consecutive in nature from some minimum number to some maximum number m. I see. That's why the answer is m last time. Okay, and then the total number of students were n. Okay, however, when Mr. Tommy completed the process, he found out there is one metric number accidentally left out from the record. Okay, and then we have the assumption here metric number are integer numbers. So you need to design a divide and conquer algorithm to identify the metric number that has not been keyed in. Okay, so you need to write a pseudocode as well as the running time complexity for your algorithm. So how do we solve this one? Class? Anybody wants to suggest to me how can we do this? We always forgot to take a break. Please remind me if you need a break. Let's just finish this one question off, and then we can end our class. I don't think it's early. Come, let's discuss this. How would you do this if you have this question? How would you do it? Class? Binary search? How would you do a binary search then? Because you don't know what is the missing number. For binary search, you need to know the key, right? So in this case, what is the key? Or can we? Unless you tweak it. Get the concept of binary search, tweak it. How would you tweak this? Maybe have the full keyed in array. Yeah, and then after that, what are you gonna do? So if let's say you have one array that with the one that is missing, and then you go and compare between the two arrays. Is that how you would do it? Yes, it is possible, because provided that the array is sorted, and you have another array for comparison. So what is the running time complexity for that one? It is possible to do that, but the running time complexity, is that the most ideal one? How about the rest? No idea. How would you tackle this problem?
Does consecutives mean one after the other, right?
1, 2, or maybe it starts with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or maybe some 900, 01, 02, 03, 04. Yeah, consecutive is like that.
So once he keyed everything in, he forgot one more number. Is that-
Yeah, he keyed everything, but he doesn't know which number he missed out. He only know that if let's say he's supposed to have 100 students, but then in the spreadsheet, it's only up until 99. But he doesn't know which metric number that he missed out.
So
That is the problem. Yeah.
we
So
could
how would you do?
sort, because when you merge sort, you have to individualize every element, right? You will know which one is kind of
Okay. The result of a merge sort is a sorted list, right? How would you use how are you trying to apply the concept of merge sort into finding the missing number, or are you planning to sort using the merge sort?
Well, I'm
in
thinking of the concept of, since you're splitting it up into their own arrays for each element.
Okay, but then how still how would you find that missing number?
But since it's already technically sorted, right? Since it's consecutive.
Okay, and
that-
but then you still don't know. You will have a sorted list, but somewhere in the middle of the array, somewhere in the array, there's one number missing. Imagine if 100, yeah, maybe you can go to what if he has 1,000? So how would you do it? How would you do it? So in the sorted array, how would you know that there's some number missing in between the numbers?
Well, since it's consecutive, you can iterate throughout the array to see if +1 doesn't exist.
Yes. So that is one way of doing it, right? So what is the running time complexity if you are using that approach?
Um,
Merge sort? Is n log n plus the n or the m that you're doing? M, right? Maximum number. N? Yeah.
maximum total number.
M log n plus n, right? Supposedly.
I think so.
Yeah. So that is one of the way. Anybody else got a different way to do it? So basically you sort it and then you check whether the current number +1, whether the next number is equal or not equal. And then you should be able to find what is the missing number, right? If it is a sorted array.
Yeah.
Okay, so that is one way. Anybody got a different way? So basically the divide and conquer is, yeah, basically you're doing the sorting as the divide and conquer, and then you do the comparison. Any other way that you can, find? Okay, what if I eliminate the requirements that you need to use divide and conquer algorithm? Is there any way that you think you can solve this problem? Class? If let's say I don't mind, you don't have to use the divide and conquer at all. Is there any other way that you probably can solve this problem? No?
Still thinking.
I know that in one of our lecture in the future, I think one of the lecture that we're going to be looking into, we are going to look into what we call the select algorithm. I think we're going to look into it in one of the topic. I don't remember which topic. Is where you can actually find the median of the element, without actually sorting it. Okay, so in a sense, you can actually check the size or something, and find the missing number, if I'm not mistaken. So that is something that maybe when we look into that algorithm, maybe perhaps we can revisit this question and see how we can solve that problem much better using the select algorithm. And yeah, and I think we can actually solve it using something else as well. I think the previous class mentioned, one of your friend in the previous class mentioned something about using counting sort for this. Do you think you can use counting sort to find a missing number? Class? So that is another, there's so many ways since we are learning algorithm, like, and we know if like let's say we sort it and then we check it, then perhaps the running time complexity will be log n n log n plus some n, let's say for example, or m log n plus n. So that would be the running time complexity. But then yeah, if like let's say for counting sort, maybe we can just like having it as a like n, maybe perhaps just to run through the one, and then you put it inside the halfway the counting sort where you try to count how many occurrence of the number, and whichever slot that is empty is the number that is missing. Do you see, class? Yeah. So it's something for you to think. So nobody is going to give me the answer here. No. So we're just going to discuss this question. Nobody have the answer. Okay. So in that case, for the last question, I'll leave it to you. Okay, to think about it. I mean, if you want to run through with me, whether that can be done, you can do so. You can just text me or something since you don't want to discuss it right now. Okay. So yeah, so I guess that's it for today. For our tutorial. Do you have any question for this topic? Are you all good?
No questions for me.
Okay. So in that case, I guess I will see you in the lecture next week. All right. Okay. Thank you everyone. Assalamualaikum warahmatullahi wabarakatuh. See you next week.
Thank you, Doctor.
Thank you,
Bye.
Doctor.
Thank you,
Let me
Doctor.
stop the recording. Bye. Assalamualaikum. Bye.